Welcome to this SAT Advanced Algebra overview. Today we will examine the discriminant of a quadratic equation. To understand the discriminant, let's start with the quadratic formula. For any standard quadratic equation, the roots are calculated using the well-known quadratic formula. The expression inside the square root is known as the discriminant, commonly denoted by the capital letter D. The value of the discriminant determines the number of real solutions the quadratic equation has. First, if the discriminant is greater than 0, the equation has two distinct real solutions. Graphically, this means the parabola crosses the x-axis at 2 points. Second, if the discriminant is exactly equal to 0, there is only one real solution. In this case, the vertex of the parabola lies directly on the x-axis, touching it at just 1 point. Finally, if the discriminant is less than 0, the equation has no real solutions because you cannot take the real square root of a negative number. Graphically, the parabola does not intersect the x-axis at all. Recognizing these three scenarios can be useful for identifying the number of roots or intersection points in quadratic problems on the SAT. Next, we will walk through 5 examples. Although these types of problems can be solved using the Desmos calculator, we will solve them using algebraic techniques to build a deeper understanding of the underlying concepts. Let's apply the discriminant to solve a typical algebra problem. We are given the quadratic equation 3x squared plus k times plus 12 is equal to 0, where k is a positive constant. The problem asks us to find the value of k that gives the equation exactly one distinct real solution. For a quadratic equation to have exactly one distinct real solution, its discriminant must be equal to 0. To proceed, we identify the coefficients from our equation, which are 3, k and 12. Now we substitute these coefficients into the discriminant formula. Simplifying this expression, we get k squared minus 144 is equal to 0. Isolating k squared, then taking the square root of both sides and remembering that the problem specifies k must be a positive constant, we find that k is equal to 12. Therefore, the correct answer is k equals 12. In this problem, we will look at how the discriminant relates to the graph of a quadratic function. We are given the function f(x) equals kx squared plus 8x plus 2, where k is a constant. If the graph of y equals f(x) has two distinct x-intercepts, we need to find which of the choices could be the value of k. Since x-intercepts correspond to the real solutions of the equation, having two distinct x-intercepts requires the discriminant to be strictly greater than 0. Next, we identify the coefficients from our function. A equals k, b is equal to 8, and c is equal to 2. Substituting these values into the inequality yields 8 squared minus 8k greater than 0. Now we simplify and solve the inequality, which reveals that k must be strictly less than 8. Looking at our given options, 5 is the only value that is less than 8. Therefore, the correct answer is A5. To determine the constraints on coefficients for a quadratic equation with no real solutions, let's look at the given equation where p is a constant. We want to find the range of possible values for p that satisfies this condition. For a quadratic equation to have no real solutions, its discriminant must be less than 0. First, we identify the coefficients by comparing our equation to the standard form here. A is equal to p, b is equal to -6, and c is equal to 3. Next, we substitute these values into the discriminant inequality, which we'll use to solve for p. Simplifying this expression, then solve for p, we get that p must be greater than 3. This matches option B, making it the correct answer. In this example, let's explore how the discriminant applies to a system containing both a quadratic and a linear equation. We are given a system of equation that has no real solutions, and we need to determine which of the given options could be the value of missing coefficient c. To find where these two equations intersect, We first set them equal to each other, yielding x squared minus 4 times plus 7 is equal to 2x plus c. Next, we rearrange this equation into standard quadratic form by subtracting 2x and c from both sides, then simplify like terms. Now, we identify the coefficients of this new quadratic equation as 1, -6, and 7 minus c. Since the system has no real solutions, the discriminant must be strictly less than 0. Substituting our coefficients into the discriminant formula, we set up an inequality which will help us find missing coefficient c. We simplify and solve for c by expanding, simplify like terms and dividing both sides by 4. We find that c must be strictly less than -2. Looking at our multiple choice options, -3 is the only value that is less than -2. Let's look at another system of equations containing a quadratic equation and a constant linear equation. We are asked to find the value of the constant c that results in exactly one real solution. We begin by setting the two equations equal to each other. To write this in standard form, we subtract c from both sides and group our constant terms. Next, we identify our coefficients of the new quadratic equation, which are -2, 12 and -10 plus c. Because the system has exactly one real solution, we set the discriminant equal to 0. Substituting our values, we get an equation which we can solve to find c. To solve for c, we expand terms, use the distributive property, simplify like terms, which will give us that c equals 8. So, our final answer is c equals 8. Understanding the discriminant of a quadratic equation is a practical way to save time and prevent calculation errors. Instead of fully solving a quadratic equation, analyzing the expression b squared minus 4ac allows you to systematically extract key properties of the equation's solutions. First, the discriminant directly determines the number of real solutions. Rather than factoring or completing the square, evaluating the sign of the discriminant tells you immediately if the equation has two distinct real roots, exactly one real root, or no real roots at all. Second, this algebraic concept translates directly to coordinate geometry on the test. The number of real solutions corresponds to the number of x-intercepts on the graph of the parabola. This tool is also highly effective for analyzing systems of equations, such as a line intersecting a parabola. By setting the two equations equal to each other and rearranging them into standard quadratic form, you can apply the discriminant to find how many times the linear and quadratic graphs intersect. Ultimately, mastering the discriminant is a valuable strategy for managing your time on the exam.